April 18, 1943. The island of Guadalcanal holds its breath beneath the weight of tropical heat. At Fighter II airstrip, little more than packed coral and crushed rock carved from jungle. 18 Lockheed P-38 Lightnings sit fueled and armed, their twin Allison engines silent in the pre-dawn stillness. The air tastes of aviation fuel and salt spray carried inland from the coast. Ground crews have worked through the night preparing these aircraft for a mission unlike any other. Extra fuel tanks hang beneath the wings, each carrying 165 additional gallons that will extend the Lightning's range to its absolute limit. In the operations tent, pilots study maps and commit coordinates to memory. Their target is not a position on the ground or a formation of enemy bombers. Their target is a single man, Admiral Isoroku Yamamoto, architect of Pearl Harbor, commander of the combined fleet, the most brilliant naval strategist Japan possesses. Intelligence has revealed his flight plan, his exact route and timing. Yamamoto will fly from Rabaul to Bougainville in a Mitsubishi G4M bomber, escorted by 60 fighters. The P-38s must fly 435 miles over open ocean, arrive at a precise moment, and execute what American planners are calling Operation Vengeance. The mission requires precision navigation over featureless sea, perfect timing, and aircraft capable of matching the Zero's performance at low altitude. Most critically, it requires fighters that can dive away from danger faster than any Japanese aircraft can follow. The P-38 Lightning possesses that capability, but only recently. Only because of a modification so simple it seems almost absurd: a pair of electrically actuated flaps, each measuring 8 inches wide and 58 inches long, mounted beneath the wings. These dive recovery flaps represent the solution to a problem that nearly doomed the Lightning as a combat aircraft. They are the result of engineering insight born from catastrophic failure. They are the wire trick that transformed a troubled design into one of the Pacific War's most feared fighters. To understand why these small flaps mattered so profoundly, one must first understand the extraordinary promise and equally extraordinary problems of the P-38 Lightning. Lockheed designed the aircraft in response to a 1937 Army Air Corps specification calling for a high-altitude interceptor capable of 360 miles per hour at 20,000 feet, with armament concentrated in the nose. The requirements were demanding enough that most manufacturers considered them impossible. Lockheed's solution was radical: a twin-engine fighter with counter-rotating propellers to eliminate torque, tricycle landing gear for better visibility during takeoff and landing, and all guns mounted in the nose where convergence issues that plagued single-engine fighters would not apply. The XP-38 first flew on January 27, 1939, and immediately demonstrated performance that exceeded specifications. On a cross-country speed run from California to New York, the prototype averaged 350 miles per hour despite multiple technical problems. The military potential was obvious. Here was a fighter that could climb faster, fly higher, and carry more firepower than any single-engine design. The twin-engine configuration provided redundancy that made long over-water flights survivable even with one engine damaged. For operations in the Pacific, where distances between islands stretched for hundreds of miles across empty ocean, this redundancy meant the difference between reaching base on one engine or ditching into shark-infested waters. But the Lightning harbored a flaw that would cost lives and nearly end the program. At high speeds, particularly in dives, the aircraft encountered aerodynamic compressibility, a phenomenon that would not be fully understood until the post-war development of supersonic flight. When the P-38 dove at speeds approaching 500 miles per hour, airflow over the wings accelerated to transonic velocities. Localized regions of supersonic flow formed shock waves that disrupted the boundary layer and caused control surfaces to lose effectiveness. Pilots reported that at high speeds, the control column became immovable. The aircraft's nose would tuck downward uncontrollably. Pulling back on the yoke produced no response. The elevator had lost all authority. The P-38 would continue diving, accelerating beyond design limits, until structural failure occurred or, if the pilot was lucky, until the aircraft descended into denser air at lower altitude, where speeds naturally decreased and control gradually returned. Many pilots were not lucky. During test flights and combat operations, P-38s were observed entering dives from which they never recovered, impacting the ground or ocean at terminal velocity while observers watched helplessly. Major Signa Gilk of the Army Air Corps became one of the first to document the problem during test flights in spring 1941. He described the terrifying sensation of complete loss of control, the violent shaking as shock waves buffeted the airframe, the certainty of death as the ground rushed upward, and nothing he did made any difference. He survived only because he had sufficient altitude to ride out the dive until reaching denser air, where control slowly returned. Not all test pilots were so fortunate. The problem was particularly acute in combat. Fighter tactics developed by American pilots emphasized energy maneuvers, using altitude advantage to dive on enemy aircraft, make a single firing pass, then zoom back to altitude using speed gained in the dive. Against Japanese fighters, which excelled at slow-speed maneuvering but lacked high-speed performance, this tactic should have been devastatingly effective. The P-38 could climb above zero formations, dive through them with guns blazing, and escape before the nimble Japanese fighters could bring their superior maneuverability to bear. But compressibility made this impossible. A P-38 pilot diving on a zero formation knew that if he dove too steeply or built up too much speed, he would lose control and likely die. This knowledge created hesitation. It forced Lightning pilots to make shallow diving attacks that gave zero pilots time to evade and counterattack. It negated the P-38's primary advantage. Japanese pilots quickly recognized the limitation. By 1942, combat reports from the South Pacific documented Japanese tactics specifically designed to exploit compressibility. When P-38s attacked from above, zero pilots would pull their aircraft into steep dives, knowing that American pilots could not safely follow. The P-38, designed to dominate through speed and altitude advantage, found itself trapped by its own aerodynamic limitations. Lockheed engineers understood they faced a problem at the bleeding edge of aerodynamic science. In 1943, the physics of transonic flight remained poorly understood. Wind tunnels could not accurately simulate conditions near the speed of sound. Theoretical models were primitive, but through systematic testing and analysis, engineers identified the mechanism. At high speeds, the wing's center of pressure shifted aft as shock waves formed. This shift created a nose-down pitching moment that overwhelmed the elevator's authority. The solution, when finally devised, was elegant in its simplicity. If the center of pressure could be shifted forward through other means, normal control effectiveness would return. The dive recovery flaps accomplished this by disrupting airflow over the outer wing sections. When deployed, the flaps created turbulence that broke up shock wave formation and shifted the center of pressure forward. Additionally, the flaps acted as speed brakes, slowing the aircraft and allowing it to descend out of the critical speed regime more quickly. The flaps were small, each measured only 8 inches by 58 inches, but positioned precisely on the outer wing sections where their effect would be maximum. They were actuated electrically through a control wire from the cockpit, requiring only that the pilot flip a switch when entering a high-speed dive. The modification was tested extensively at Lockheed's Burbank facility in late 1943. Test pilots reported immediate and dramatic improvement. With dive flaps deployed, the P-38 could be dived to its structural limits without loss of control. Recovery was smooth and predictable. The nose-down tuck disappeared. Pilots could make full deflection attacks on ground targets or enemy aircraft and pull out safely at the last moment. But getting the modification to operational units in the Pacific proved more challenging than developing it. Late in 1943, Lockheed assembled several hundred field modification kits, complete packages containing the flaps, actuators, wiring, and installation instructions. These kits were shipped to forward bases in North Africa, Europe, and the Pacific where maintenance personnel would install them on operational P-38s. The Pacific-bound shipment, however, encountered disaster. In March 1944, a transport aircraft carrying 200 dive flap kits intended for P-38 units in the Pacific was shot down by friendly fire in a tragic case of mistaken identification. The kits were lost. Replacement kits would not arrive for months. Pacific P-38 units continued operating without dive flaps through much of 1944, still vulnerable, but some units received the modification earlier, and the effect on combat effectiveness was immediately apparent. The 475th Fighter Group, operating from bases in New Guinea, began receiving P-38s equipped with dive recovery flaps in early 1944. Pilots who had previously exercised caution in diving attacks now pressed attacks with confidence. Combat reports documented successful engagements against Japanese aircraft at altitudes and speeds where earlier encounters had been inconclusive or resulted in P-38 losses. The flaps restored what the P-38 had been designed to do: dominate through energy advantage. Japanese pilots who had learned they could escape P-38s by diving discovered that this tactic no longer worked. American pilots could now follow them down, maintain control, and continue firing throughout the dive. The psychological impact on Japanese aircrew was profound. The Zero had been designed around different principles than American fighters. Japanese engineers, working under severe weight constraints imposed by limited engine power, had created an aircraft optimized for maneuverability and range at the expense of everything else. The Zero lacked armor protection. It lacked self-sealing fuel tanks. Its structure, built from lightweight aluminum alloys, could not withstand the stresses of high-speed flight. But within its performance envelope, the Zero was magnificent. At speeds below 300 miles per hour, it could outturn any Allied fighter. Its rate of climb was exceptional. Its range, over 1,600 miles with drop tanks, allowed operations far from bases. Early in the Pacific War, these characteristics made the Zero legendary. Allied pilots who engaged Zeros in turning dogfights usually died. The Zero could reverse direction faster, could sustain tighter turns, could climb away when damaged. But as the war progressed, American pilots learned to avoid the Zero's strengths and exploit its weaknesses. The key was speed. At velocities above 350 miles per hour, the Zero's control surfaces became increasingly heavy. Ailerons required tremendous force to move. The aircraft could not roll quickly. And in dives, the Zero's light structure made high-speed maneuvering dangerous. Pilots attempting violent maneuvers at high speed risked structural failure. The wings might fold. The control surfaces might tear off. Japanese training emphasized that the Zero must never be dived beyond certain speed limits. Pilots were taught to avoid high-speed combat, to keep engagements in the slow-speed regime where the Zero's superiority was absolute. American tactics exploited this limitation ruthlessly. The Thatch Weave, developed by U.S. Navy Commander John Thatch, used pairs of fighters covering each other in scissors maneuvers that prevented Zeros from sustaining advantageous positions. Boom and zoom tactics, perfected by Marine and Army Air Forces pilots, used altitude to dive on Zero formations, make high-speed firing passes, then zoom back to altitude before Zeros could respond. These tactics worked with any American fighter that had speed advantage: F-4U Corsairs, F-6F Hellcats, P-47 Thunderbolts. But they worked best with the P-38 Lightning, once the dive recovery flaps eliminated compressibility. The transformation was not merely tactical, but psychological. Japanese pilots had entered the war supremely confident in their aircraft and training. The Zero's early victories over British Brewster Buffaloes and American P-40 Warhawks seemed to confirm Japanese technical and tactical superiority. But the appearance of later-generation American fighters, heavily armed, heavily armored, faster in straight-line flight and in dives, challenged assumptions about Japanese invincibility. By 1943, experienced Japanese pilots recognized they were fighting with obsolescent equipment against an enemy whose industrial capacity allowed constant improvement and replacement. The Zero they flew in 1943 was essentially the same aircraft that had attacked Pearl Harbor. But the Americans were flying P-38s, F-4Us, P-47s, new designs with performance the Zero could not match. And American factories were producing these aircraft by the thousands, while Japanese production struggled to replace combat losses. The psychological burden of this disparity weighed heavily on Japanese aircrew. They knew that skill and determination alone could not overcome the material advantages their enemy possessed. They knew that every mission might be their last, not because they lacked courage or ability, but because their aircraft were simply outclassed. The dive recovery flaps represented this disparity in miniature. The modification was simple, a pair of electrically actuated panels, some wiring, a switch in the cockpit. The installation required perhaps 40 hours of labor by maintenance personnel. Yet this simple modification transformed the P-38's combat effectiveness completely. It solved a problem that had threatened to ground the entire Lightning force. And it did so through systematic engineering analysis and technological innovation, precisely the kind of problem-solving approach at which American industry excelled. For Japanese engineers struggling with limited resources and insufficient research facilities, such rapid problem-solving was increasingly impossible. They identified the Zero's shortcomings clearly enough. They knew it needed armor, self-sealing tanks, more powerful engines, higher speed performance. But implementing improvements required time, materials, and manufacturing capacity that Japan no longer possessed. The A6M5 Model Zero, introduced in 1943, featured slightly better performance and some protection improvements, but remained fundamentally the same aircraft. Plans for the A7M Reppu replacement fighter languished in development hell, delayed by engine problems and resource shortages. The Reppu would not enter service before the war ended. Meanwhile, American fighters kept improving. Each new variant brought better performance, heavier armament, longer range. The mission to intercept Admiral Yamamoto demonstrated what the P-38, properly configured and properly employed, could accomplish. On that April morning in 1943, 18 Lightnings took off from Guadalcanal and flew 435 miles at wave-top altitude, navigating by dead reckoning over featureless ocean, timing their arrival to coincide exactly with Yamamoto's bomber and its escort reaching Bougainville. The navigation alone represented an extraordinary feat. One of the P-38 pilots, Captain Thomas Lanfear, later described the tension of the long over-water flight, the constant monitoring of fuel consumption, the nagging fear that navigation errors might send them past the interception point without ever seeing their target, the awareness that they were at extreme range, and any combat damage that forced them to burn extra fuel would mean ditching in the ocean. They found Yamamoto's flight exactly where intelligence predicted. Two Mitsubishi G4M bombers escorted by 6 Zeros, flying low over the jungle. The P-38 split, 4 aircraft climbing to engage the Zero escort, while the remaining 14 dove on the bombers. Captain Lanfear and Lieutenant Rex Barber made the killing passes, both pilots later claiming credit for shooting down the Admiral's aircraft. The bomber crashed into the jungle. Yamamoto died on impact. The Japanese retrieved his body the next day and confirmed his death. For Japan, the loss was catastrophic. Yamamoto had been the combined fleet's most capable commander, the architect of Japan's naval strategy, the one leader whose tactical and strategic insight had repeatedly outmaneuvered Allied forces. His death left a void that could not be filled. The mission succeeded because the P-38s could do what no other Allied fighter could: fly the distance required, fight effectively at low altitude where the Zeros were strongest, and escape through speed when necessary. The dive recovery flaps played a crucial role. When Zero pilots attempted to dive away after losing the initial engagement, pursuing P-38s followed them down without hesitation, maintaining control throughout the dive, keeping Zero fighters under continuous pressure until the Japanese escort broke off and fled. This was exactly the kind of engagement that had been impossible before dive flaps. Japanese pilots who survived the mission reported that the American fighters seemed unnaturally fast in dives, that they could not be escaped through the diving maneuvers that previously worked against P-38s. The modification had transformed the Lightning from a troubled design into a weapon that could execute precision strikes against the most heavily defended targets. By late 1944, as more P-38 units in the Pacific received dive recovery flaps, the aircraft's combat record improved dramatically. The 475th Fighter Group, the Satan's Angels, became one of the highest-scoring American fighter groups in the Pacific, with pilots like Major Richard Bong and Major Thomas McGuire accumulating kill totals that exceeded any other American aces. Both men flew P-38s equipped with dive recovery flaps. Both credited the modification with giving them confidence to press attacks that would have been suicidal in earlier models. The recurring sound that came to symbolize American technological adaptation was the distinctive whistle of the P-38's turbo superchargers, a sound unlike any other fighter of the war. Japanese soldiers and airmen learned to recognize it instantly. Unlike most American fighters with loud, rasping exhaust notes, the Lightning's turbo-superchargers muffled engine noise and produced instead a high-pitched whistle that carried for miles. Japanese troops on the ground would hear that sound and know that P-38s were overhead, likely preparing to strafe or bomb their positions. Japanese pilots would hear it and know that American fighters with superior speed and altitude capability were in the area. The sound became associated with American air superiority, with the relentless pressure that American air power exerted across the Pacific theater. It was a sound that announced not just the presence of individual aircraft, but the vast industrial and technological apparatus behind them. Every P-38 represented tens of thousands of hours of labor, millions of dollars in resources, and systematic engineering problem-solving that allowed American forces to identify deficiencies and correct them rapidly. The dive recovery flaps were the visible symbol of this capability, a simple modification that solved a complex problem and restored the P-38 to its intended role. For the Japanese pilots who faced P-38s in combat, the experience represented a slow awakening to realities they had not anticipated at the war's beginning. They had expected to face enemies inferior in skill and equipment. They had assumed that Japanese martial spirit and superior training would overcome American industrial advantages. By 1943, these assumptions had collapsed under the weight of accumulated evidence. American pilots were not inferior. American equipment was not second-rate. An American industry could solve problems faster than Japanese forces could exploit them. The P-38's compressibility issue should have been a permanent vulnerability, a flaw that Japanese pilots could exploit throughout the war. Instead, American engineers identified the problem, developed a solution, manufactured modification kits, and distributed them to operational units within months. This kind of responsive innovation was precisely what Japan's rigid, resource-constrained military-industrial complex could not match. Japanese aircraft designers knew their designs had shortcomings. They submitted proposals for improved models. But getting those proposals approved, funded, manufactured, and fielded took years, time the Japanese military did not have. The contrast between what Japanese military planners had expected and what they actually experienced in combat against the P-38 could not have been more stark. In the opening months of the war, Japanese forces achieved victories so swift and complete they seemed to validate every assumption about American weakness and Japanese superiority. The destruction of battleships at Pearl Harbor, the conquest of the Philippines, the capture of Singapore. These victories suggested a war that would be won quickly through tactical brilliance and spiritual determination. Japanese propaganda emphasized that Americans were soft, corrupted by materialism and democracy, lacking the discipline necessary for modern warfare. When Japanese pilots first encountered P-38s in late 1942, the Lightning's compressibility problems seemed to confirm these assumptions. Here was an American fighter with impressive specifications on paper, but fatal flaws in practice. Pilots who survived combat against early model Lightnings reported that the twin-engine American fighter could be defeated by diving away, forcing the P-38 to either break off or lose control. This was exactly the kind of technical inadequacy that Japanese propaganda predicted. But within months, the situation reversed. P-38s with dive recovery flaps began appearing in combat. Suddenly, the diving escape tactic no longer worked. American pilots pursued zero formations through dives, maintaining control and firing effectiveness, while Japanese pilots struggled with control surfaces that were never designed for high-speed combat. The shock was not merely tactical, but ideological. It demonstrated that American forces could adapt faster than Japanese forces could exploit weaknesses. By war's end, the P-38 Lightning had compiled an extraordinary combat record in the Pacific theater. American pilots flying Lightnings claimed more than 1,800 Japanese aircraft destroyed, with top aces like Richard Bong crediting the P-38's combination of range, firepower, and, after dive flaps were installed, maneuverability with their success. The aircraft's ability to escort bombers to distant targets, to hunt enemy aircraft over their own bases, and to execute precision ground attack missions made it indispensable to Pacific operations. But the Lightning's success rested on a foundation that Japanese forces could not replicate. When the P-38 encountered compressibility problems, American engineers identified the issue, tested solutions, manufactured correction kits, and fielded the modification within months. This cycle of problem identification and solution represented American military-industrial capability at its best. The dive recovery flaps themselves were not sophisticated technology. They were simple aerodynamic surfaces actuated by electric motors through control wires, a wire trick in the most literal sense. But implementing this simple solution required research facilities to identify the problem, engineering expertise to design the modification, manufacturing capacity to produce thousands of modification kits, and logistics networks to distribute them to forward combat units scattered across the Pacific. Every step in this process represented institutional capabilities that Japan, by 1943, no longer possessed in adequate measure. The final irony of the P-38's troubled development and ultimate success lies in what it revealed about different approaches to military aviation. Japanese engineers had designed the Zero to maximize performance within severe constraints. They had succeeded brilliantly, creating an aircraft that dominated the Pacific skies for nearly 2 years. But the Zero's virtues were also its limitations. Every design decision that improved maneuverability or range came at the cost of structural strength, pilot protection, or high-speed performance. The design was optimized so completely for its specific mission that adapting it to changed circumstances proved nearly impossible. American engineers approached aircraft design differently. The P-38 was overbuilt by Japanese standards, carrying armor and redundant systems that added weight and reduced raw performance. But this conservative approach to structural design meant the aircraft could be modified, improved, and adapted as combat experience revealed necessary changes. The dive recovery flaps were just one modification among many that improved the Lightning's combat effectiveness. Pilots in the field reported that cockpit heating was inadequate at high altitude, so Lockheed developed improved heating systems. Aileron control at high speeds was too heavy, so engineers designed powered boost systems. The turbo-superchargers suffered from intercooler problems in tropical climates, so improved cooling systems were developed and retrofitted. Each modification took time and resources. Each required systematic testing, but each improved the aircraft's combat effectiveness incrementally. The cumulative effect of these improvements transformed the Lightning from a troubled design with serious flaws into one of the war's most effective multi-role fighters. For the young American pilots who flew P-38s in combat against Japanese forces, the dive recovery flaps represented more than just a technical improvement. They represented the tangible proof that the vast industrial system behind them was responsive to their needs, was actively working to give them every possible advantage, was treating their survival as a priority rather than an acceptable cost of operation. As the war in the Pacific ground toward its inevitable conclusion, the P-38 Lightning continued evolving. Later models featured still more improvements, better engines, increased ammunition capacity, refined aerodynamics. But the dive recovery flaps remained perhaps the single most important modification, the simple wire trick that solved the problem threatening to ground the entire program. Those small panels, 8 inches wide, 58 inches long, electrically actuated through control wires, represented in miniature the systematic problem-solving approach that characterized American military-industrial might. They were the visible symbol of a broader truth, that in modern warfare, victory comes not merely from courage or tactical brilliance, but from the capacity to identify problems, develop solutions, manufacture improvements, and implement them faster than one's enemy can adapt. This was the shock that Japanese military planners experienced gradually and painfully throughout the Pacific War. Not the dramatic sudden reversal of fortune, but the slow realization that they faced an opponent whose advantages were structural and systemic, whose capacity to solve problems exceeded Japan's capacity to create them, whose industrial base could sustain losses and continue improving while Japanese capabilities steadily eroded. The whistle of P-38 turbo-superchargers overhead, that distinctive sound that carried across tropical islands and announced American air superiority, became the audible symbol of this asymmetry. Every Lightning that flew combat missions represented not just an individual aircraft, but an entire ecosystem of technological capability. And those small dive recovery flaps, deployed with a simple flip of a switch when entering a dive, represented the specific innovation that allowed the Lightning to fully exploit American advantages while negating Japanese strengths. They were proof that simple solutions often matter more than sophisticated ones, that identifying the right problem is harder than implementing the solution, and that systematic engineering approach, unglamorous and methodical, wins wars more reliably than dramatic technical breakthroughs. This was the lesson the dive recovery flaps taught, written across Pacific skies in contrails and gun camera footage, proven in combat results that could not be disputed. The P-38 Lightning, properly modified and properly employed, could defeat the Zero not because it was more maneuverable or more elegant, but because it could dive faster, climb higher, hit harder, and operate farther from base than any aircraft Japan could field. And it could do these things because behind every P-38 stood industrial and engineering systems capable of solving problems as they emerged rather than accepting limitations as permanent. The sun sets over the Pacific, casting long shadows across coral airstrips where P-38s sit silent, their combat missions complete. The war has ended. The innovations that made victory possible, the dive recovery flaps and countless other modifications large and small, will fade into technical history, understood mainly by historians and aviation enthusiasts. But the lesson they teach remains relevant across decades and conflicts. Wars are won not merely by courage or sacrifice, though both are necessary. They are won by systems, industrial, technological, logistical, that can identify problems faster than enemies create them, can develop solutions faster than enemies adapt, can implement improvements faster than enemies can respond. The dive recovery flaps represented this systemic advantage in its simplest form. A wire trick that saved lives, restored combat effectiveness, and allowed American pilots to fully exploit their aircraft's potential. It was not glamorous. It was not celebrated in propaganda. It was simply effective. And in war, effectiveness matters more than elegance. Results matter more than intentions, and the capacity to solve problems systematically matters more than any single brilliant innovation. That is the truth the P-38's dive recovery flaps demonstrated across Pacific skies. That is the lesson written in the combat records of pilots who flew Lightnings against Zeros and survived because someone, somewhere in the vast American military-industrial complex, had identified a problem and developed a simple solution. The wire trick that let P-38s defeat the Zero was never just about wires or flaps. It was about the difference between systems that could adapt and systems that could not. And in the crucible of combat, that difference determined everything.